an example comparing different compounding periods to the crown jewel of compounding periods, continuous compounding. What we have here and in this first equation, in this first graph, is our normal compounding interest formula with a variable in the place of the number of compounding periods. So we're going to assume a 5% interest rate, and for the sake of simplicity, we're going to assume an initial principal of $1,000, and then this 6 is going to represent the number of years. I just chose an arbitrary number. That number could be anything depending on the need of the formula. But this X is taking place of the number of compounding periods. So if we were to go to regular 1 year, every year compounding interest, we would anticipate that at the end of that time period, we would have approximately $1,340 and about 10 cents. If we elected to go to 2 compounding periods, so every 6 months we did the compounding, we would be up to $1,344 and about 89 cents. And then if we elected to go quarterly, we should anticipate continuing increase in the amount because we're earning that interest on top of the interest, and we're up to $1,347. You can see from the direction of this graph and the shape that it takes here in the first quadrant that the rate of increase is getting shallower and shallower. We are not increasing at the same rate that we were at the very beginning. We're seeing sharp increases at the very beginning where we flatten out as the compounding periods become much more realistic. Every couple months, maybe every month. And we could scale this out to see that. But what we're really interested in is the upper limit of this graph. You can already start to see that it's starting to flatten out. And for the purposes of Desmos and the window that I have set up, you're barely getting any kind of growth as if you would go from 4 compounding periods to 5. And really, that difference would be negligible, just a few cents, but obviously that builds on itself, and maybe it'll be worth your while to increase the number of compounding periods. So again, the crown jewel is this second equation. No compounding periods necessary in here because it assumes that you are continuously compounding. We still have our 5% interest rate, we still have our 6 years, we still have our $1,000, and because there's no variable, you can already see that we have a dollar amount that we know is our upper limit. That's $13.49 and 86 cents. If I include this graph in the visual, you can see how the original graph just is going to run alongside that horizontal line as an asymptote. And even if we go out to a place where maybe the detail on Desmos isn't strong enough to show us both of them, if we go out to say, let's go compounding monthly, which would be x is equal to 12, and we zoom in, we can still see a difference between them of approximately, that's $13.49.86, $13.49.01, approximately like 85-cent difference. Not a lot of money when you're talking about being in the 1300s, but still a difference. And if we were to scale this out even farther, they would run together a little bit more. There we're up to 10 cents versus our known 86 cents. So as you scale it out, the difference becomes a little bit less. But we do have that upper limit on what is the absolute maximum that we can expect, assuming that we can continuously compound and use this function instead of our original compounding formula to determine that amount.